So now that we've looked at ways to create mathematical models to get equilibrium constants, or more specifically, in our case for ligand binding constants, let's come back and look at how do we get rate constants. And so remember, the goal is to get time dependencies, where we can look as the start of a study, we can look at how much product do we form over time. If we see a curve like this, we can see what the time dependence is of product formation, but then how do we actually interpret this? So the way we get information out of plots like this is to use different types of rate equations. And so one of the first that we're going to look at are integrated rate equations. And so these are really simple mathematical models that you may have seen in general chemistry. And so we're going to start with a really simple reaction where A is converted to B. This is the product. And note that this is not an equilibrium arrow. So what this implies that this is just that this reaction is irreversible. And so we only give one rate constant to this. Okay? And so let's define our parameters. So initial, we have initial concentrations, and we have concentrations at time t. And in this case, we're just going to look at A naught, that's the initial, and at any time t, A naught is going to be equal to the concentration of A remaining at time t plus the concentration of that A converted to the product B at any time t. So note the difference in the subscripts here. Okay. So looking at the equation, what we see is that we can think of a rate, for instance. So remember, rate is going to be equal to the rate constant. So in this case, K1 times the concentration of the reactant at any time t. So K1 AT, all right, in this case. If we define the rate, so we're going to define the rate in this case as the consumption of A over time t. Okay? And actually, if we define it in this way, then we have to look at the equation, and we note that over time, A is going to be lost and converted into B. So actually, we need to give this a sign. So the equation actually becomes dA dt equals negative K1 times A at any given t. Okay? First thing we need to do is rearrange this because we're going to integrate this equation. So we need to divide by, so first we multiply by dt on both sides, and we also divide by AT. Okay, that converts into an equation that looks like this. Actually, we'll start this higher. dA t over AT equals negative K1, note the negative stays there, times dt. We're going to integrate both sides. That's going to give us something in the form of ln, the natural log of A at any time t over the initial concentration of A equals K1, negative K1 times T plus C. Okay? And I'm not going to show this, but C is 0, so this goes away. And what we end up with is a final equation where if we take the exponent on both sides, we get at any time t, concentration of A is going to be equal to the initial concentration of A times e to the negative k1 times t. Okay? And so what that looks like then is if we plot the concentration of A, we get an equation that looks like this. We get, or excuse me, nope, not correct. It's consumption of A, so we start at an initial concentration of A naught, and we have an exponential decay, which approaches 0 as time increases. Now, we can also, as I stated before, we typically like to follow the formation of product B to avoid any interference from side reactions. So we can convert this equation V of t equals A naught 1 minus e to the negative k1 times t. And so if we follow the production of B instead, that follows this type of shape, again, where this approaches the concentration A naught. Because in this case, A naught is converted to B in a stoichiometric fashion, so 1-to-1 or a 1-to-1 stoichiometry. So if there's a different stoichiometry, this asymptote might be different. At any rate, this tells you what if we had data that was following a first-order equation, such as this, for this type of reaction, we could fit this equation to this and extract the rate constant, K1, from this. Now, for this type of data, using this type of plot, we would have to use a nonlinear regression in order to fit that. And in the next video, I'll quickly show you how to linearize this.